Good afternoon. Could you hear me? Yeah. When we do the online session, I need your feedback. Okay. Right. So today we will continue the theory of computation second part. So before that, I will give a small recap on the previous session. Right. Okay. So in the previous session, we discussed about this theory of computation, right? So which is about that we know that with the computation with the computers we use discrete system, right? So I think at the very first lesson of this module I explain you what is continuous signals and discrete signals, right? So in computers we use ones and zeros, so which means we have discrete signals. So these uh, digital any digital device we call them as uh, discrete system, right? Because they can understand ones and zeros. Now when we design these systems, we need to evaluate the capabilities of these systems, right? But with the computers, when it comes to computers, their behavior change dynamically, right? So it is quite complex to evaluate the capability of these kind of systems. So that is the study of that, how to evaluate the capability of discrete system is we call as theory of computation, right? So this is actually now, so far we have learned most of the sections like hardware components, right? So that's very straightforward. We can understand what is happening over there. But here it is from the software perspective, right? So we know a computer or machine, any laptop or smartphone, it's a combination of hardware and computer software, right? So how the software capabilities we evaluate, right? So the in fundamental level, this is what we call as theory of computation, right? Then we move to the automata. Automata is like one section that we discuss in the theory of computation. So here we discuss about the now the in theory of computation we evaluate some abstract machines, right? So here this automata is self-operating machines. That means once you give the instructions, it can follow the instructions and do uh, step by step, right? So how we can instruct, right? So now when it's come to hardware component, we know how the CPU get the instructions, how it is fetched, and all these things we have discussed, right? But when you write a program, computer program, right? So you are giving a set of instructions. How this computer can understand these instructions, right? So that's what we discuss over here. So what we do is we give the instructions through a language that this machine can understand, right? So we know we use natural languages for communication purpose. Similar way, we use a predefined language to instruct these abstract machines, right? So if an abstract machine is instruct with a language, we call it as automata, right? Where it can operate, self-operate. Then we now what we're doing is we narrow down our studies to some specific area because it's a large area where it's very complex. So we narrow down our studies to a specific area where we can understand simpler things, right? So now from automata, we comes to the finite automata. So automata is self operating machine, right? So in this machine, behave dynamically. So when it's dynamically behave, its states change, right? So these changing states, if the changing states are finite, we call it as finite automata, right? So the machine, this kind of machines, change its states when it's receive inputs, right? So its current state change with the input and change its next state, right? So likewise, it's continue changing until it's reached its goal, right? Okay. Then we discuss some of the applications of finite automata. So we all, without knowing, we all using the applications of this kind of automata, right? So when you do the search and also when you compile or interpret your programs that you write, these kind of machines are using, right? Then we discuss about the two types of finite automata, right? So there's one called deterministic finite automata, other one is non-deterministic finite automata. So last session, we learned how to construct a DFA, right? Yeah. And also we learn about the alphabet, right? So now we are talking about machines which can understand the languages. So to define the language, we need some alphabet, right? So alphabets are again kind of a symbol or images. So we define our alphabet, and from that particular alphabet, we take symbols and define our language. So when it comes to language, in any language, in even natural language, we have words, right? So in technically we call them as strings. So these strings are made up with the alphabet characters that we define. So with the strings, the each language have predefined words, right? So like uh, in natural languages, even though some languages have same alphabet, their words are different, right? So they use different words. So some words are valid in the one language, maybe not valid in another language, right? So in the here we call them as strings, right? Right. Next, we learn how we can design a DFA, deterministic finite automata, which accept the language of uh, given language, right? Okay. So this finite automata we represent with states with circles, and we have arrows to show the transitions, and also we represent our input alphabet, right? So that is one way that we can represent state machines, the sorry, finite automata. Another way is using this set of sets, right? So here we define our now our machines, right? So these machines, like I think I explain you how it works with a vendor machine, right? So vendor machine or washing machine, anything, if you think about that, they have different states, right? So likewise, our these finite automata machines have some finite number of states. So these states we call as Q set, right? And also we have to define an input, right? So that input alphabet we define as sigma. Then how this machine react for given input. So that's we call it as a transition function, right? So like I think you all learn about mathematical functions, right? So how when we give the independent variable value, how the dependent variable value change. So similar way, when we give an input symbol, how the current states of the machine change, right? What is the new state? So this is what we call as transition function, right? And the Q0 is the start state, right? So this start state is one element that have taken from this Q, right? And also we have some fire acceptance states. That means uh, the that's also again comes from this Q sets. So if a word reach to the final state, so that we say that that string is accepted by this machine, right? So we discussed couple of examples. I'm not going to go through them today. Okay, so today we will move to new section, non-deterministic finite automata. Right. So let me share my slides with you. Okay. Can you see my slides? Yeah. Can you confirm that you can see? Okay. Right. Right. So now, under non-deterministic finite automata, we learn how we can design the non-deterministic finite automata machine, and also we will write the states transition diagram. Right. We learn uh, how we can create the table, and also we convert our NFA, non-deterministic finite automata, to a DFA, right? So every NFA will have equivalent DFA. So we see how we can create this equivalent DFA. All right, right. So now non-deterministic finite automata. So non-deterministic finite automata, again, it's a finite state machine, right? But here, when we compare with the DFA, the difference is in the DFA, now we know these machines, uh, when they receive an input, their current state change, right? So in deterministic finite automata machines, we have to define the next state for every input simple. So that means, let's say our input alphabet is with ones and zeros, right? So I think you can understand what I mean, right? So last time we discussed how we can define the alphabets, right? So if we have the alphabet with ones and zeros, and we are designing a machine, a DFA, deterministic finite automata, we have to define for every state, right? So let's say we have three states. So each three states, we have to define what will happen if it's received input A, 1, right? So what will happen if it's received an input 0? So each state, we have to determine what will happen if it's received this particular character, right? So since our alphabet has two characters, so we have to check only ones and zeros, right? So if you have around 5 characters, you have to determine for every single character what will happen to the current state of the machine, right? So you have to do for every single state what happened for each input symbol, right? So the deterministic finite automata machine is quite complex, right? So when you look at that, there are a lot of arrows going here and there, right? But when it comes to non-deterministic finite automata, we have less conditions, right? So it does not have, it can have, but it is not a must to have states. It's not must to define the next states for every input symbol, right? So it can define or maybe without defining, so we can keep, right? And in DFA, for one input symbol, let's say it's 0, for 0, if the our state is Q0, the transition, that means next state is only 1. So if when the machine is in the Q0 state, if it's received an input 0, it can go only Q1 or Q2 or one particular state, right? So it can't go for multiple state, right? So that's the conditions comes with the DFA. But when it comes non-deterministic finite automata, it could go to multiple states, right? So it could have a state or it may not having a state. So very flexible in a non-deterministic finite automata, right? Okay, let me explain with a diagram, right? So when you see this diagram, you can see here NFA. In NFA, it is in NFA here we have we have the same number of states Q0, Q1. Here also we have Q0 and Q1, right? Here in the end of, let's first look at the DFA, right? So if you look at the DFA, you can see that for the Q1, now this assume this state machine is for alphabet which has characters ones and zeros, right? So this 1 and 0, right, for Q1 is defined, right? So it is defined what happened when input symbol is 0, when the state is Q0, right? It will go to the Q1. So the current state is in Q1, and if it's received an input symbol 1, then it will be in the same state, right? So it's defined. And similar way, Q1, if it is in the Q1 and if it's received input symbol 1, it will be self-looping, right? The same thing happened to the 0. So for 1 and 0, both it's self-loop, right? So here we don't see any multiple states for one symbol, one input symbol, right? For 0, only one state. For 1, only one state. And also all the input symbols are defined, right? So this one also, 1 also defined, 0 also defined. Right? So when it comes to NFA, Q0. For Q0, if you give input symbol 0, what happens? it will self looping with Q0 and also it will go to Q1, right? So it has multiple transitions. And if you give 1 when the state is Q0, what happens? It is not defined, right? It is not defined. If you go to Q1, right? So Q1, when the input symbol is 0, it is not defined, right? Q1, when the input symbol is 1, then it's moved to Q0, right? So this is the difference between NFA and DFA, right? So I think it is clear for you. Do you have any question on that? If you want to clarify anything, you can ask, you can speak up, or you can share through the chat box. Either way. Seems like no problem. Oh, everyone is sleeping. What's going on? Hmm? Okay. So I assume you don't have any problem. It's very clear for you all, right? Okay. Okay, let's move on. Right. Right. So like now, when you represent the DFA, deterministic finite automata, we use two ways, right? So one is with a state machine. That means we use the circles and arrows to represent the states and the transitions and everything. Other thing is states transition table, right? With these couple of sets. Now, similar way, we can define the non-deterministic finite automata also, right? So we have same set of uh, tuples, right? So we have Q4 set of states and sigma for input alphabet and Q0 for start states and final states and the transition function, right? Okay. So you might think about why we don't have any final states over here, right? So this is just an illustration purpose. I have put it does not represent any language, right? So that's why it does not have any final states. So if we have a final states, we represent it with double circle, right? So here you don't see any double circle because it's just to differentiate the NFA properties of NFA and the DFA, right? Okay. Right. Now, let's start with some exercises, right? So design a NFA that accepts elements of language L. So the language L is defined with strings. Okay. So these strings, like this is a mathematical notations, right? So when we define functions, we use this kind of notations, right? So this says when the language is L, so it belongs the W's, right? So this W have uh, characters from the alphabet sigma, and this W should start with 0. That's a condition, right? So how we can define a NFA for this to accept this language? Okay, since it's first one, I will show you how to do it, right? The first thing is we define couple of strings that will accept by this language, right? So the words should start with 0, right? So we start from the smallest word, right? So in natural language also we have words strings with one character, right? In English we have I, and two characters, am, is, right? And three characters. So likewise, these languages also have words with different length. Only thing is we have to check whether it satisfies the given condition, right? So our condition is the word should start with 0. So we try to write few strings, right, which satisfy this condition. The first one, the smallest one is 0, right? So next we can write 00, right? So we also can write 01, but we can't write 11 or 10 because it doesn't satisfy this condition, right? So then we move to 3 length, right? So we little increase the length. Now we have 3 characters. So we write something that start with 0, right? So it could be 001 or 011 or triple zero. So we just write few examples, right? Then we want to design our NFA, right? So when you design an NFA, this is quite easy, right? So maybe you remember how we define the DFA, right? So there we have to check every possible way that the state changes, right? So here not the case, right? Here it is very simple. So this is our NFA, right? So let me explain it. So it says it should start with 0, right? So this is our start state, right? Start set. Usually we put it says Q0 or otherwise we have to have a here we can have an arrow over here, right? Yeah. Okay, so this it doesn't looks like an arrow, right? You can see it as an arrow. Okay. We have an arrow. Too big. Arrow head is too big, right? So anyway, we have to have, usually we have a short, small arrow to represent this is the start state, right? Okay. Then our condition is very simple. It says just start with 0, right? So if you want to accept this language, right? So it start from this, and the next state it should accept because the length is 1, right? So our input symbol should be what is this? So there is a question: is NF and DFA same? So I'm not clear about the question. If you can send it back, right? Okay. Yeah. Right. Okay. So hope you can see the slides now. Now we first check with our first word, right? So our word is zero. So if the word is length with one, then it should be accepted in the next state, right? So we write in the next state as our final state, right? And after that, now this is something like not only zero, right? It can start from zero and end with zero or one. So we can self loop the B as zero and one, right? So this is enough for us to design the NFA, right? So we don't have to bother whether what happens for input symbol one when the current state is at A, right? So that's not necessary. So if you check the second word, right? So let's say these words are accepted with the machine that we design, right? So our second word is zero zero. So that means it comes to the zero A, right? It goes to B, and again it will end at the B, right? So how do we find out whether the particular word is accepted? Is that should end at the final state, right? Sometimes some words or strings they go through the final state, but they don't end at the final state. So then we don't say it is accepted by that particular machine, right? Okay. So if you say 0, 0, 1, right? So it is 0, 0, and 1, right? Let's take 0, 1, 1. It is 0, 1, and 1, right? So this is acceptable by all the words which start with 0, right? Okay. Now you have few questions, right? Can you try this? So I give you 5 minutes to try this. Yeah. For the NFA, like if you define few words, right? So what you have to, how we can make sure that what the states that we have defined is enough or not, we can first, as we did in the previous example, first we identify what are the words, right? So what are the words that this particular language accepts. Then we have to make sure that you don't have to do all the possible, like it's not practically we can do, right? But you can just try with maximum 3 lengths or 4 lengths words and see whether those words are accepted by that machine, right? So if it's acceptable, then that's the final machine, right? And also you can check whether the rejected ones are rejecting. That means now in the previous one, right? The previous one, here, here, now it should start with 0, right? So if you take a word 1 and 0, right? It shouldn't accept. So if you take 1 and 0, it's not going in this path, right? So that means it's not accepted. So anything start from 1, it's not going through this path. So we can verify that it won't accepted by this machine, right? Okay. So try this. Tip the states. I think what do you mean by is can you draw from Q0 to Q3? Yes, you can draw, right? If it's like when we do the other questions, like when we convert from uh, when we convert the NFA to DFA, so we can uh, see that not always that it's from start from Q1 and going in order. Sometimes they go here and there, right? So I think when towards the end of the lesson, you will understand, right? Okay. Yeah. Right. Did you identify what are the strings that will be accepted? So how many words or strings that we can make from 0 and 1? How many possible combinations are there? 4. Yes. Right? So we have 4 combinations. So that means 0, 0, 0, 1, 1, 0, and 1, 1. Right? Okay. So each string has the length of 2. Right? So if you have the length of 1, a state machine will have minimum 2 states, right? Because we have to have a start state and the final state, right? Now, in this question, our strings has length of 2. So that means a state machine should have 3 states, right? So it's very simple. I think you can understand, right? So it should, we can have only these four strings, right? So we can't have self loop because it is not unlimited set of words, right? So the previous examples, our acceptable words or acceptable strings is the list is infinite, right? So we could create many possible words, but here it's not the case. There are only four words, right? So any other word should not accept. So how we can do is, we can't have any self loop over here. If you have the self loop, then that means we could have many repetitions. So right, so we can, like, with the self loop, it is undefined, not undefined, indefinite, uh, infinite words we can create, right? So here we have only exactly three states: start state, right? So this could be the 0 or 1, right? And again, this could be the 0 or 1. That's it, right? Now you have another question. Can you try this? Okay. Let's see how we can draw this, right? Right. So here what you have to do is design an NFA to detect every element that starts with 0 and ends with either 0 or 1, right? The letters except the first and last should always be 1, right? So that first letter should be 0 and the last one should be either 0 and 1, and the except the first letter, the other letters should be always 1, right? So here, the middle one, we put a self loop, right? So it would be 1 if we get 1. So what are the acceptable strings that we can have for this? We can have 0, 0, right? Or 0, 1. So those are the smallest strings that could have. And we can have 0, 1, 0 or 0, 1, 1, right? So if you take the words that has two characters, 0, 0, it's possible. 0, 1, also possible, right? So if you go for 3 letters, 0, 1, 0, can. Okay, 0, 1, 1, also possible, right? Okay, but we can't have 1, 0. So if you start from 1, 0, it is not going in this path, right? So it won't be acceptable by this language, right? So since this is NFA, we don't have to define the input symbol 1, right? It's not necessary. If it is DFA, then definitely you should define all the possible input symbol. For every possible input symbol, you have to define the next step, right? Since it is NFA, we don't have to. Okay. Right. Now, let's see how we can create the transition diagram for this same question, right? So the same question, only one change you can see is I have changed this state names, right? The states as not Q0, Q1, Q2. So for the simplicity, I put them as A, B, C, right? So I think we have done one example the last session, how we can draw the states transition diagram, right? It's very straightforward. We have 3 columns. The first column, we mention all of our states, right? So we have 3 states, A, B, C. Then if you have 2 input characters in your alphabet, then you have to have 2 more columns. If you have 3, you have to have 3, right? So it depends on the number of characters in your alphabet, right? So here we have 0 and 1. Now uh, we interpret our state diagram to a state transition diagram, right? So we start from the A. So when the current state is A, it's it get input symbol as 0, then its transition is towards B. Right? So when you start from the current state of A, it's received input 0, then it's changed state change to the B, right? So that's how we mentioned over here. Then for the input symbol 1, we don't have anything, right? So it is not defined. If it is not defined, we put it as pi, right? So this is the symbol for pi. So this is the standard way how we represent, right? If it is not defined. Then that's all the possible input symbol. Then we go to state B, right? So when the state B, the second row, for the input symbol 0, for the input symbol 0, it go to C, right? So for input symbol 0, it go to C. For input symbol 1, it stay it stay on B or it move to C, right? So since it is NFA, we can have multiple transition for a one input symbol, right? So we write it as B comma C, right? So it should go to B and C, either B or either C. Next, we check the state C, right? So the state C, you can see here you have a star, right? So that means this is a final state. So you can represent it in the state transition diagram by a star or by circle this character, right? Okay. So when it's goes to C, it's not defined, right? For both input symbol, it is not defined. So either 0 or 1 is not defined. So we represent them as 5, right? Okay. So this is a diagram for our NFA, right? Okay. Mm, uh, right. Now let's see how we can define this NFA. Now, at the beginning, I said now any NFA, any non-deterministic finite automata has an equivalent DFA, right? So usually designing a DFA is quite complex because we have to think about we can't have any multiple transitions. We have to think about every possible transitions, right? So there are so many conditions to be satisfied. But designing an NFA is very easy. So what we do is we design NFA and convert it to a DFA, right? So that's how usually we do. So the process is first we define the NFA, then we draw the state transition diagram of NFA. By looking at the state transition diagram of NFA, we can create the state transition diagram of DFA, right? Then looking at the table, we can design our DFA state machine, right? So that is the process from NFA to DFA, right? So first we start from designing the DFA state machine, sorry, NFA state machine, and we obtain our NFA table, right? From the NFA table, we create our DFA table. From the DFA table, we design our state machine diagram, right? Okay. Now, I have explained you how to obtain this NFA table, right? So now from this NFA, we see how we can get this DFA table, right? Okay, start from the first one. So we start from the start state, right? So our start state is A, right? So here we have A. So if we give 0 for A, it goes to B, right? So we write it as B. Then for if the current state is A and the input symbol is 1, then it is not defined, right? It is 5. So we write here again 5, right? Okay. Now we have moved from A to, we move to B and nothing, right? Pi is nothing, right? Not any state. Now next from B to, we need to move forward, right? So we get the B. When you have B, if it gets 0 as input symbol, it's transit to the state C, right? From B, it goes to C. Then when it's get 1, when the current state is 0, B, and when the input symbol is 1, it has 2 states, B and C, right? So in our DFA, we write it as a new state, right? You can see here, I write it as BC, right? So it's represent a new state. Now from A, we move to B, and from B, we go to C and BC, right? So the BC is a new state, right? So we don't know how it works. So here, for the current state, we add a new state as a BC, right? So this is something extra that is not in your NFA state machine, right? Now, with the BC, we check what happened for the input symbol 0 and input symbol 1, right? So we go to NFA table for B and C, right? So now we have to take the union. I think you all remember the sets. Union means the total, right? So we have to get the union of B and C. So for the B, when you give 0, it goes to C. For the C, it's nothing, right? So final answer is goes to C, right? So we can write here C. Then next we have to check what happened for the BC current state when it's received the input symbol 1. So when it's received input symbol 1, that means this column, right? For the B and C both, it will go to B, C, and nowhere, right? So B, C, and nowhere. That means finally it goes to B and C. So we have a new state called BC. So we can write it as BC, right? Okay. Then now we from B it goes to BC. So we define the BC. Now from B it goes to C, right? So we have to define the C. So we get the C. I have done a small mistake. Since now here you can see a star, right? So the star is because this C is final state, right? And this BC also a final state because every states which include the final state should be the final state. Now, what I mean was the in our NFA final state is C. So in DFA, if you define any new state that includes the final states of NFA, then that's again a final state in DFA, right? So that means here BC also should be a final state. So this DFA will have two final state. One is BC and other one is C. Is that clear? Or you want me to explain? Right. So now what we check is C, right? For the C, if it gets 0, nowhere, right? So we have defined it as pi. And for the 1, again, it is pi, right? So we define all as pi, right? Okay. So this is our DFA. Okay. So someone requests to explain the BC row, right? So let me explain again. Now, with this, right? With this, we identify this, there are multiple transitions, right? That means it goes to B. When our current state is at B and we receive, so when I'm in B and if I receive input symbol as 1, it goes to B and C, right? So that BC is a something new state. So we have to define the new row for that, right? So now in the BC, now we have to check what happened when the input symbol 0. So what do you mean by this BC? BC means this, when you check the transition, you have to check the transition of both B and C, right? So when you fill this one, we have to check what happened to the B and C both states when it gets the input symbol 0, right? So we go to this table. When the state is B and given the input is 0, it go to C, right? That's not enough. We have to check C also because this is new state BC. So when the state is C, when the input symbol is 0, it goes nowhere, right? So finally, we can say this one final state is C, right? So here, what do you mean by BC is you have to get the union of B and C, right? So union means either B or C, right? Both you have to get. Then when you come to the input symbol 1, right? We get the input symbol 1. Now our again, we have to check for both B and C, right? B and C. Now for the B, it is BC. For the B itself, it is BC, right? For the C, there's no transition. So Since for the B, it is BC, we write here, it says BC, right? Okay. And for the C, we don't have anything, so we write 5, right? Okay. Okay. Right. Now let's see how we can draw our diagram, our DFA with the state transition diagram of DFA, right? So this one, this diagram I have copied over here, right? So here you can see you have only 4 rows, but here we have 5 rows because this pi is again in DFA we have to consider as another state because the DFA now we can't have undeterministic state, right? So this pi is the state where A goes for the input symbol A. So we can't just keep as nothing like in NFA because it's against the definition of DFA. In definition DFA, we have to have a state for every single input symbol. So for the pi, again, we define a new state, right? So that's why I have uh, entered a new row and set it as pi, 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 right? Okay. Let's see how we can draw this, right? We start from A, our start state, right? So with start state, now, even though you can see here BC, right? So this is not now multiple states. This is one particular state, right? So here you can see I have put a comma, right? B comma C. But here it is BC. That means it is one single state. Here it means either B or C, right? So that's the difference. Now here for the A when it's received the input 0, it go to the state B, right? So we start from A. Now we start very fresh uh, state diagram, forget about the NFA, and we start from the beginning, right? So we start a new state and name it as A and give the input symbol 0. That's supposed to be, right? So we draw another circle and name it as B. Then for the input symbol 1, it's a new pi, right? So I said now this pi we can't ignore in DFA. So what did I do? New one, new state, right? So here we have A, B, C and all. So D, right? It could be any character. So we put D. For the D, for when the state A, the input symbol is 1, it goes to D, right? Clear. Then next one, can you try that? The BC. Just take 2 minutes and see whether how you can continue this. Okay, I give you 3 minutes for you to complete this looking at that, right? So after that, I can explain my answer with you. Okay. Okay, so we have done the first row. Let's see the second row. Right. Now, in the second row, we have to move forward from the state B, right? For the state B, if the input symbol is 0, it moves to C, right? So we draw a new state C, where it's go from B to C, right? And when it's received the input symbol 1, it goes to another state called BC, right? So for the simplicity, I write it as BC. If you want, you can replace it with a new character like E or F or anything, right? But at the beginning, it's better to have like BC so you won't get confused. And with the final state diagram, you can, if you want, you can change it with a new character, right? So now here we keep it as BC. The next, we have to check this BC, right? Right. For the BC, now it's again another state, right? So when it's received the signal input symbol as 0, it go to C, and when it's received 1, it will be in the same state. So we put a self loop over here, right? Okay. Since this include C, this will be one final state, right? So we use double circle for the BC. The next we see what happened when the current state is C, right? So when the current state is C, and if it's received symbol 0, it will go to our D state, which means that pi state, right? And again, for the input symbol 1, it goes to the same state, right? So that's why with the same curve, we mention it is 0 and 1, right? Then we have one more row. So for pi state or our D state, for 0 and 1, it will be at the same place, right? Because it's nowhere, right? So that's why we put it the self flow, right? You may remember that we were talking about dead state, right? When we were designing DFA. So this can be kind of a dead state, right? Okay. Right. So I hope you can understand this, right? So can you try this? First, you draw an FA and draw the state diagram, right? Then draw the, sorry, first draw the state diagram for the NFA, then draw the state transition table for NFA, then look at that and draw the state transition table for the DFA, then final state diagram, right? So I give you 5 minutes to try this. second character, right? So if you say cat, 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 so A is the second last character. All right. So this is the NFA for the given question, right? So in this question, all the accepted string should have at least minimum length of 2, right? So second last character. So that means we can have either 1, 0, right? So from the last, second character, right? So 1, 0 also possible. 1, 1 also possible. But 0, 0 or 0, 1 cannot be accepted, right? And we can have 0, 1, 0 and 1, 1, 0, right? Okay. So this is the states transition diagram, right? So we have 3 states, A, B, C. C is our final state, so we put a star. And from A, when it's received 0, it goes to A. When it's received 1, it goes to A and B, right? And for B, when it's received C, 0, it goes to C. When it's received 1, again it goes to C, right? So C, we haven't mentioned any states, right? Okay. So this is the DFA, states transition diagram, that equivalent to this NFA, right? So here, you can see now, we start from A, right? For the A, we have 0, then it goes to A, right? For A, if it receives 1, it goes to A and B. So we write a new state as AB, right? Right. Now from here, now once you write the first row, then we look at the states that we have, because that's how we proceed, right? So we start from one state, it's direct to 1 or 2 states. From them, then it's branch and go further. So here our state A is directed to again A and another state called AB, right? So A is already there. So we write the AB, right? For the AB, we come this come to the NFA table and check how it works, right? For the AB, that means you have to check A and B both, right? Union of A and B, A or B, right? So either A or B. Now for the input symbol 0, it goes to A or C, right? So we write it as AC. For the input symbol 1, it goes to A, B, C, right? So we write A, B, C. Now we have two more new states, AC and ABC, right? So we write AC here and check how it works, right? So AC means you have to check from the A and C, right? For the A, it is A. For the C, it's nowhere. So that means the final answer is A, right? For the input symbol 1, AC, A, it is AB. For C, 5, right? So final answer is AB, AB, right? Now we have AB already over here. So we don't have to define a new states, right? So if it is something totally new that you don't have already, you have to add a new row and continue. That's how it works, right? Now we define AC, but we haven't defined ABC. So we write a new row ABC, right? So in the AC, C is included. So we set it as one final state, right? Now we check ABC. Give me 1 second.
അമ്മേ അമ്മേ അയ്യോ അമ്മേ
Okay. For the ABC, right? The ABC, we have to check ABC, right? For the input symbol 0, it goes to A and C, right? So that means the whole column we have to consider, right? So we write AC. And for the input symbol 1, it goes to A, B, C, right? So we write here A, B, C, right? So all the states that's included in the 0 and 1 column already defined over here, right? So that's the end of the diagram, the state transition table. Otherwise, you have to continue, right? So if you find any new state over here, you have to again define them, right? Now this ABC includes C, so it is a, final state, right? Right. So you see how we can draw the DFA, right? So we start from A, the same table with 4 columns, sorry, 4 rows. I have copied over here, right? Now for A, it goes to A and AB, right? For 0, it's at A, and for the 1, it goes to AB, right? The next one, AB. When it's received 0, it goes to AC, right? So we define a state called AC. And for the 1, it goes to ABC. So we direct it to ABC, right? The next one, it is AC, right? So AC is a final state. So we have the double circle, and when it's received 0, it goes to 1, right? So when it's received 0, it goes to, sorry, A. And when it's received 1, it goes to AB. So when it's received 1, it goes to AB. Here, again, you have ABC, right? So it is again include the C. So we draw the double circle. And for the input symbol 0, it goes to AC. And input symbol 1, self-looping within the ABC, right? So this is our final DFA. Now, if you compare this picture, this diagram with this one, right? So you can see this one is quite complex, right? So you can directly draw like we did in the last class, but when you do this way, you don't skip any steps, right? So it's very uh, straightforward method that you can clearly draw the particular DFA. But the DFA, there is only one unique DFA, right? You can have multiple different types of DFA. There's only one DFA, right? Okay. Okay, how to get the AB, AC, and ABC, all these combinations, right? So all these combination, it is not like we randomly taken, right? So if I go back to that, now this AB, ABC, all that is the next state that we look at this table and only we define, right? So if I say here, I say you how we get the AB. AB comes because here when you your state is A and give the input symbol 1, it goes to A and B both. It goes to A and B, right? So that's what AB, right? So here it's that means it's a totally new state we have to define. So for the simplicity, I name it as AB because then for us easy to map, right? So you can try it with a different symbol if it is confusing, but I prefer this way because that's direct me to how to complete the table, right? If you prefer a different symbols. So AB means another character like C, we can get a C, a D, E, or F, right? So that does not have to be AB, but since it's AB, I named as AB, right? So AC, ABC, similar way, right? So you can, if you want, you can say like, let's say, you can say it as D, right? So if you write this as D, you can write this as a D, right? Then for the AC, you can say it as F. Let's say J, some numbers, some characters, right? So then this also J. For ABC, now this should be D. For ABC, this also should be J. ABC, we can say another one H, H, right? So just a symbol. Okay, I think it's clear. Hope it's clear for you. It? Okay. Then so how do we determine whether we need to self transfer or not. So now, now here see, when you have ABC, right? So it says it is ABC. So that means the same state. So we can define it as it's self looping, right? So that's how we define it. Okay. Right. So that's the end of this lesson, right? Uh, so I wanted to do a couple of some OS question also, but yeah, I have to wrap up the session now. I will share with some solved examples, solved questions, right? So you can go through them. Something that same thing that what we have learned, but I wanted to do one or two questions with OS. We couldn't do some questions, right? Because of we you had some events those days, so we couldn't have some sessions. Anyway, so before your exam, I will share some solved questions in the model, right? So go through them and also go through the past papers. Then it won't be easy. It won't be difficult, right? Okay. Uh, yeah. So that's the end of this module, right? So I wish you all the best for your exams, right? So if you have any questions, you can just drop me an email if you need to